I want to say that right now I'm still absorbing the next round of information about ZK stuff. Uh, so in particular, one of the things that I'm looking at is zero knowledge proofs about statements about matrix multiplication. And part of the reason, pardon me, for looking at that is because linear algebra is blazingly fast on modern architectures, and this kind of thing is at the heart. So-called doubly efficient ZK proofs about linear algebra, if my understanding is correct, is at the heart of things like Zcash. So I'm absorbing that information, but I'm also thinking a lot about the relationship between zero knowledge and OSLF. So in particular, OSLF gives you a wide range of statements you can make about models of computation. And so you'd like to be able to say when you can have zero knowledge proofs of the statements that you can make from these logics that are generated. And how that relates to a wide variety of complexity classes. So you would like to be able to say things about when statements in the generated type system live in NP, when they live in IP, the class of interactive proofs, and know therefore that because these statements live in those complexity classes, that you can generate zero knowledge proofs. And this is interesting because now you're generating logics. You're now using the logics to reason about complexity aspects and security aspects. And I anticipated the complexity questions. I hadn't anticipated how they would connect with the zero knowledge side of security. So this is turning out to be quite an interesting investigation. I don't have results to report, but I'm just letting you know the direction of my thinking. So it appears that there's a whole gamut of algorithmic things that the OSLF algorithms ought to be able to help us satisfy or investigate. Again, from an algorithmic perspective, without having so much of this stuff is done by hand, right? So if you look at the zero knowledge literature, it's littered with a bunch of recipes, like the sum check protocol, the RK protocol, and GR protocol, these kinds of things. So the point is that we don't want a cookbook full of recipes. What we want is to know how to cook, and then you can make up your own recipes. And so that's sort of part of the direction that OSLF is all about, and coming to grips with the implications for complexity theory is looking, it's turning out to be a much bigger vista than I had anticipated, which is great news. It's really interesting. I can also just quickly show some progress that we're making on the proof theory side of this as relates to resources. It's still very early days, but things are tightening up. So I think I've shown this paper before. Let me hit screen share. But things are tightening up. So again, this in terms of the generation of the proof theory, the thought is to investigate the simplest of these kinds of systems. So so we're in general, you can do these for algebraic theories with rewrites. Rewrites could potentially be on lots of things. We want to restrict attention to rewrites on bipartite terms. So these are terms that are built from constructors with two arguments. So an example would be the par of the row calculus, right? So when you have a par of an input and an output, then that rewrites. Similarly, with lambda, when you have the application of a lambda abstraction to a lambda term, that rewrites. So this kind of bipartite kind of system can be thought of as dividing the world into program and environment. So without too much loss of generality, we're talking about dividing the world into the part that is suspended. So this is the function part in lambda, or the input part in row, and then that part of the world that's providing the information that is necessary to unsuspend the computation. Now the interesting point is that it's completely dual, right? You could flip it round, and you could say, when you have that the suspended part is the environment, and the offering of the data part is the program. So this kind of duality gives rise to an interesting way of carving up the world that looks a lot like linear logic. And if you then insist, like the blockchain does, like our chain does, like Ethereum does, that that rewrites require a resource. You don't get to just rewrite for free. You have to pony up a resource. Then that gives you a kind of linearity that allows you to relatively faithfully encode a lot of what's going on in linear logic. So that's kind of the idea, and then you can, and then the proof rules sort of write themselves. So that's kind of one. So again, with OSLF, there's a kind of model theoretic point of view, and then there's a proof theoretic point of view. The proof theoretic point of view is novel in the sense that the what we normally think of as cut rules in proof theory. So what do I mean by that? So in standard intuitionistic logic, the idea is that if I have an implication, so A implies B, and I have something that establishes A. So let's say I have a proof of A implies B, and I have a proof of A. then I should be able to kind of cut those two together to establish a proof of B, right? So I'm kind of applying the proof of A arrow B to the proof of A to get a proof of B. That should be reminiscent of something, right? Reminiscent of beta reduction. And in fact, that is the case. So the thought is that if one were doing the proof theory right, then you would also have rules like that cut rule for each of the different kinds of red X's. So in the case of the row calculus, it's not application. You have a proof of something like this is a par that has an input, but we don't know what the output term is. Or this is a par. Yeah, so think about it this way. This is a par that has an input, but we don't know what the output is, but we can specify some information about it. We can constrain the kind of output terms that we're willing to accept. Or dually, this is a par that has an output, but we don't know what the input term is, but we can constrain it. We have some extra information. And then you can kind of apply the proof of that to a proof that, say in the first case where you've got an input, but you don't have the exact output. But but now you've got a proof that a particular output term matches the constraints on the output terms that you're willing to slot into the hole in the parallel composition. So then you can kind of apply those, apply the one to the other and get a proof of the reduction is going to be of a particular type. So that's the idea, is that you get new kinds of proofs that are in fact have cut rules that line up exactly with the rewrites of the system. And then since you have this resource that is constraining all rewrites, you can get what's called a cut elimination theorem that terminates. So without the resource, you can get cut elimination. So if you've done this right, your proofs there's a kind of rewrite on the proofs themselves that correspond to the rewrites on the terms. So that part makes sense. But you don't have you don't necessarily have termination, because the rewrites on the terms might not terminate. So, but once we resource constrain everything, then as you get rid of the resources, then your ability to rewrite terms reduces until finally you have no resources, and so the system comes to a stop until you add more resources. So just like the blockchain, right? Same kind of construction, only now we're threading this through any kind. We're providing a mechanism that works for any kind of model of computation. So you can take JavaScript and you can turn it into something that is blockchainable, or you can take some other model, and the JVM, and make it blockchainable. And at the same time, you get a logic that tells you how your program will evolve as you spend your resources. So this is clearly useful, but it also lines up with the standard theory of logic. It takes its imprimatur from, you know, Genson's original results with the Genson sequent calculus. So that's the background. I know that was a lot of information. Did any of that make sense?
Yeah, I think I can follow. I just wanted to ask you about one specific thing. So you mentioned, you compared lambda with A, and A implies B. And this is clear to me. It's like applying the function. But when you explain this in row terms, I was thinking you will say, oh, I have an input and which accepts A, and I have and returns B.
Yeah, but that's not how row works, right? Row doesn't provide you functions. An input doesn't have a return. There's no return value.
Yeah, I see.
So
you can maybe say you can say if you accept A and also another channel to return.
Yeah,
B.
but now you're trying to fit it into the functional model. But
I see.
You don't need to do that. That's kind of what I'm arguing. Is
okay.
There's a much better way to think about this, and the better way to think about this is rely guarantee. Okay, so here's the idea in a nutshell. It's these two equations out of which everything else is generated. So to understand these two equations, the context is someone provides us with a Levier theory, some higher, or it's actually going to be some higher algebraic theory. So it's Levier theories with some exponentials, not necessarily all exponentials, but some exponentials, so that you can model things like abstraction in the lambda calculus or guarded input in the row calculus. And then we're going to explicitly model the rewrites by adding the Levier adding to the Levier theory a graph theory. So you'll have some rules about sources and targets, right? So you start with your Levier theory, and then you're going to add some function symbols S and T that go from term to term, and some additional equations. The source of the source is the same as the target of the source, which is S, and that comes from the fact that we're interpreting every term itself as a, in terms of self loops. And so the source of the target is the same as the target of the target, which is the target, right? So that we're interpreting the terms as having identity loops. So these equations allow you to encode a directed graph that's associated with the rewrite rules. So you have to say for a given term what the source is for the rewrite rules. So for example, in SKI, the rewrite rule is S applied to X applied to Y applied to Z is going to rewrite to X applied to Z applied to Y applied to Z. So that's the standard S rule. So that means the source of sigma, where sigma is the rewrite constructor, is going to be that, and the target is going to be that. Right. So that's the first step. So we add these source and target symbols to our theory, and then we add a resource symbol to our theory, which allows us to constrain rewrites. And we're going to assume that we've got some term constructor K, which is bipartite, right? It takes two T's, right? And we only have source and targets with respect to K's. Okay, that's where the rewrite lives, right? And everything else is might have some contextual rewrites, but this is where the rewrite stuff happens, is in K. And so K is going to have, we insist that K have identities. So K may not be commutative, like in the case of lambda, it's not commutative, it is in par. When it is commutative, the identities will coincide. And then it may have some other constants like 0, or some other constants, C. But at least it has the left and right identities. And in some cases, it may not have, like in lambda has a left identity, but doesn't have a right identity. So we're insisting that at least have one of these identities, and when it's commutative, the two identities coincide. So that's kind of the requirements of the system. So you give us this. Go ahead.
Are you implying that when we have K with two terms, that they will definitely make a rewrite, or possibly make a rewrite?
Possibly make a rewrite.
Okay.
Okay, so now we're going to introduce a lollipop. And again, sorry, one more thing. So we started with a higher order, higher algebraic theory, right? So some Levier theory with abstraction, and some notion of rewriting, and then to this we encoded the rewrite parts in terms of these source and target symbols, and then we added the resource. So that's what we've got going. Now for the higher order algebraic theory, we've got lambda notation. So the idea is that a term of this form is really just a context. So we're just using the lambda notation to make it easier to manage the contexts. Okay, so that's the basic apparatus, and now we're going to define an arrow. Okay, so this is our arrow, and we're using the linear lollipop. We subscript it by K because it's going to involve the K-based rewrites. When it's clear in context, we get rid of the subscript. And because K is not commutative, or not necessarily commutative, there are two directions of this arrow, right? It's determining whether the hole is in the right-hand side of the K or the hole is in the left-hand side of the K. And so now, another piece of the puzzle that is directly related to the ongoing debate that Christian and Mike and I have. Christian and Mike, were able to kind of give a good categorical account using sets as the collection, but they don't know how to do the general thing where you don't have sets as the collection. And this, is staring them in the face as soon as they try to model something like the parsimonious lambda calculus, where it doesn't have, where it has term constructors that are not products. It has some tensors. And it has the exponential operator. Okay, so, but for purposes of our discussion, we're going to simplify that aspect of the research and say that we're going to collect our the meaning of our formulae, as always, are going to be the collection of witnesses that satisfy the formulae. So in this case, where the witnesses are going to be contexts. So they're not closed terms. They're terms with a hole in them. So it's all the context U, such that U is really an abstraction of K with T. So there's some T, and if you build K with T in the left-hand side and you give resource to that, so it's ready to do a rewrite, but it's suspended, waiting on the term. So that's the other thing is with this idea is because you now have two ways to suspend. You can suspend by withholding the resource, and you can suspend by withholding a term. The nice thing is when you withhold the resource, you get the other linear operators. So you turn the k into a tensor because k is not going anywhere without the resource. So if you deny the resource, then you have a k of two terms that are not moving forward. And so you can potentially extract those terms. But you may not have projections, so that's why we call it a tensor as opposed to a product. So anyway, so that's the basic idea. So this thing is locked and loaded, so to speak, but it's missing a term. And for any u prime, so there exists some t prime that allows that makes u look like this, that allows us to decompose u into this shape. And for any u prime in tau, so the meanings of taus are always going to be sets like this, and u prime has to come from the left hand side of the arrow. So for any u prime that comes from the left-hand side of the arrow, if I plug it into the hole, so that's there. So this is the application part. So I'm applying u, which has this shape, and we're insisting that u has this shape. When I plug it into the hole, so it fits the shape of the hole, it fits the shape of the context, right? So if you remember my introduction, what I was saying was we have some constraints on either the output or the input. That's what tau is providing, is the constraints on what we're putting into this hole. So we don't know specifically what goes in this hole, but we have some guidance. All right, so for any u prime that satisfies this guidance or follows the guidance, when we put it into the hole, if there is a rewrite, then what we rewrite to is of type tau prime. So you see, we don't have, so in the case of the row thing, let's say we're sitting there waiting on an input, and we have some guidance as to the kind of output term we're allowed to fill the hole with. Then when we rewrite, we know that what we're going to be left with is a continuation with a particular substitution, right? So that continuation, which is not a value, but a program, is going to be of type tau prime. And in fact, it works the other way around, right? So instead of having an input for t, let's say we have an output for t, and then we have some guidance or constraints on how we fill the hole with an input term. So all the input guarded terms, u prime, that fulfill the guidance, that follow the guidance, we put it, this thing here would be put that input term in par with the output term that we were given. And if that rewrites, and so in other words, the channels match. So it will rewrite to V, and V will satisfy tau prime, right? So in other words, the continuation of the input term that followed the guidance tau will somehow satisfy tau prime. So you see, it's not about input and output. It's about the shape of the term itself. So if you want a visualization of this, the kind of types you were talking about, which is the type theory and that has dominated programming practice, is at the level, if you think about a circuit board, it's at the level of, do the pins match? Do the pins match the spec?
I see. So,
Right?
so basically, I was talking about in R space perspective. I was talking about some specific value on a channel, and you are saying no, the whole R space.
That's right. That's right. Yeah. And
Mhm,
again, so
mhm.
if we go with the
See.
if we go with the hardware example, instead of matching the pins, you match whole chips.
Mhm, mhm,
You say whatever component we're going to plug into this part here, it has to satisfy a spec,
mhm.
which
Yeah,
might
yeah.
include information constraints across what happens amongst the pins. You say
I see.
at this pin, this is happening, and over here at this other pin, this is not happening, right? That's the
Mhm,
kind of thing you can say when you take this whole component perspective. So that's the idea, and
mhm,
so now your type system looks remarkably like linear logic, but it has some extra stuff in it. So this, because we're talking about sets, we automatically get these first four things. So this union is the or. We write it as a union to
mhm.
emphasize the fact that it came from sets. And likewise, this empty is the false, and we write it as empty to emphasize that all of this stuff came from sets. So these first four operators are just ordinary intuitionistic logic coming from sets. And then all of your and then the structural stuff that's from here out to here, all of this stuff comes from directly from the structure of our theory. And then we have context types. And here we have to be quite careful. We're only we don't allow so we allow nesting in the left and right, but we're sort of careful about the way we don't say that a closed term is a context essentially. So contexts don't give you closed terms. So we build this up somewhat conscientiously. So you have and this is it turns out that this is exactly the same as the modal interpretation. So this is actually a kind of modality, and if you carefully compare this to Milner's original the Hennessy-Milner logics, this coincides with the modal operator. So the theorem that we will eventually prove is that this gives us a way to link the Hennessy-Milner style logics to the linear logics in a canonical fashion. So remember, we're now going to generate a vast number of logics. So every model of computation is going to get its own logic. But there's actually going to be two flavors of this. One is going to be this linear style, and the other flavor is going to be the Hennessy-Milner style, where you have necessity and possibility operators. So this operator here, this lollipop, which we've given model theoretically up here, is going to turn out to be it's a rely guarantee. So it's going to be a necessity operator. We're going to interpret rely guarantee in terms of necessity. So that's the link. So what that does is it answers the question, the open research question: how do you relate the session types to the Chi-race types? So this answers that question once and for all for an infinite family of logics. So then you get abbreviations. So the linear perp, the linear negation is just going to be lollipop to the right identity. You'll also get another kind of negation, which is lollipop to the empty set. And then you have the duals, right? Since it may not be commutative and you may have a left identity, then you'll get uh, an arrow this way, so we just kind of put the diacritic on the left hand side as opposed to the right hand side.
Can you say what does it mean to go tau to empty?
Well, you can just look it up here, right? So now tau prime is empty. So what was that? Go ahead.
Oh, I'm thinking that we did all of the reductions and we don't have any term left.
That's one way to think about it. The other way is to say that there's no rewrite rules. You can't rewrite.
Oh, empty doesn't mean. Oh, empty means there is no rewrite rules.
That's right.
But that doesn't mean that like
it just means that the thing is inert, no matter what you put in that context.
Okay.
When you constrain it in a certain way. So I've got my T here, but I'm going to put some constraints on this so that it can't interact with this. So for example, this thing is listening on X, but all of these things don't listen on X. They don't output on X. Maybe they output on Y or Z or whatever, but they don't output on X. Since they don't, this is inert.
Yeah. I see.
Yeah.
And what does it mean to negate this kind of term?
So the important thing is there are two kinds of negation. There's linear negation, which has to do with do you terminate? And there is set negation, which has to do with taking complements.
I see. And can we somehow make negation of? I mean, I'm trying to think about negation of a term which doesn't have rewrite rules. How we can negate and create rewrite rules?
So, no.
That makes sense.
No, that's again interesting question. What you're asking is, if I do this kind of negation, then if I follow it with this kind of negation, what does that mean? And it's very straightforward. We just follow the semantics. So this is going to ensure that we have the things that you that are inert, the things that are inert with respect to tau. They don't interact with taus. And then you negate that via complement, then you would get those things which do interact with taus.
Oh, so basically we are just matching and creating a new term which has rewrite rules.
No. You're it's I don't know how to say it. Think of the universe of terms is out there already. All programs are already out there. They've all been written, and these logics carve up all programs that ever will be written into chunks, into collections, pieces.
Oh, I see. Yeah, I'm thinking about some kind of that we have some R space and with.
Yeah, no. But, this is dealing with the space of all programs.
Okay.
Okay, so then the term formation stuff is all very, 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 very straightforward, right? So each constant is going to have its own type, and then with your once you introduce context, then you have to have a kind of axiom thing, a wire. So given that X is of type tau, you can conclude that X is of type tau, right? So, and then you can the only interesting thing here is that you notice that you can form K's this way, and it's the same K, right? And so you and in fact it's the same hypothesis. So you're declaring an intent. So these these types are intentional, right? You're saying, yes, I have a K, but I want to interpret it in this way. You know, yes, I have a K, but I want to interpret it in this way. So that's the way to think about these rules. So when I declare it this way, I'm insisting that it has, you know, it's being used in a particular way. So when I build up other terms, this will give me guidance as to places where I can put it and places where I can't. And then of course, there are some cut rules, but we won't go into that just now because this is the more important thing. The more important thing is these rules here. I'll just look at this one and then stop. So suppose that given gamma and that x is of type tau, I have that rkt of x is of type rk top tau. And then as a side condition, it can't be on this line because we're never going to, well, at least as formulated currently, we don't have a way to produce a condition like this as the bottom of a proof rule. So it couldn't be a top because we couldn't compose it. It's a side condition. And the side condition is just taken from our arrow definitions up here, right? So given that this typing context says that rkt of x is of type rk top tau, and then on the side we have to check that for all the u in tau, if I put u into the rkt, if that rewrites to v, the v is of type tau prime. So that's our side condition. Then we get to conclude that if I abstract over the x, so I get rid of the x from the typing context and I put a lambda here, that this now gives us a context, tau arrow tau prime. That's the idea. And so now we have cut rules. You can cut a lambda against a lollipop, right? And so that will that will do the thing that you expect, right? So we have a proof of the lollipopness of this lambda, and it's expecting a lollipop, and we have a separate proof that u is of type tau. And so when you cut them together, you combine the two contexts here, and you get that this is of type r tau prime, right? So we've advanced.
So this is like a rewrite to rewrite transformation.
It's the transformation of the rewrite. Yeah. You're
okay.
Yeah, you're applying the rewrite. So it's really just a generalization of the ordinary cut rule to allow for a single step rewrite. That's what it's doing. So that's the. Anyway, there's still tons of work to be done on this. One of the things that is quite interesting about this is that so this gives us intuitionistic linear logic. So it's clean and clear intuitionistic linear logic. But in order to do the classical linear logic, the higher order algebraic theory it's hard to see how to apply it. Although this weekend, I did have the insight that you can potentially build a higher order algebraic theory in which you have two kinds of variables. You have two copies of the variable set. So you bifurcate the variable namespace into a positive side and a negative side. And then what you have to do is, in the theory, you have to link the two together. so that you build these linear you build these linear higher order theories where you use the positive and the negative variables. They're linked together, and they can only be used once and exactly in this polarized way. So this is a thought that I've had about how to modify higher order algebraic theories to do what we're doing here. Is what originally I had done this, where instead of using the higher order algebraic stuff to manage the contexts, I used holes. I used contextual holes. And here, when we move from the having an axiom like this to the linear classical axiom, what we do is we color the fact that the hole came from the left-hand side, and then our proofs are well formed if we've got this kind of lineup between the holes. So the terms are really just packaging over the holes. And so they have to make sure that whatever management they do, they don't interfere with the fact that you've got to link, a hole like this, a black hole with a white hole, like that. So that's the idea. And so it occurred to me that we might be able to mimic that structure if we do the higher order algebraic theory, in which we have two kinds of variables, and then we do the linking that way. So I'll be talking that through with Mike to see if we can make this idea fly to get the classical side. But anyway, this is the kind of progress that we're making on the OSLF on the proof theoretic side. So it's a lot of fun. There's still tons and tons of work to be done, but you can see that we're making real material progress.
Yeah, and it's much more clear to me now than from your previous explanation. Now I see like different perspectives. So, yeah.
Cool. Good.
So,
go ahead.
I was going to say, I have a question that's kind of tangentially related to context and types, but deals with the existing Erlang implementation. Somebody reported a bug on dotget, and Tomislav has been responding to him. I can share screen if you want briefly.
Okay.
The thing is that dotget in this code, is everybody able to see this? So dotget becomes indeterminate. What I'm wondering is, since we are really, our focus is on correct by construct contracts, maybe should we have a dotget, or should we actually have a dotget or else as the only get function? And the dot, or does that confuse the whole machinery around the reflection and everything else if we get into a dotget or else type of a construct as opposed to a dotget construct?
So you have to understand that the dotget is really just importing functionality from a lower, essentially from Scala.
But Scala has a dotget or else. Should we just?
But this is just operation. Yeah.
Go ahead after you, Thomas.
I just want to say that this get is operation on the map.
Yeah, exactly. So it doesn't. It's like you can have both. You can have a dotget and you can have a dotget or else. You can do either one.
Mm.
What's going on with this bug is just that we haven't handled the case where there's no value correctly.
Yeah, this X is a problem.
Right, but the thing is, if I were to do a dotget or else on this, it opens up a situation where, for example, the or else could be defined as a Boolean, could be defined as of some type, right? So I'm wondering if the dotget or else would work. I have not tried it myself, but does anybody know if it would work, or we need to think through that as to if you are potentially generating?
Yeah, so you have to you have to understand that there's as long as you don't have dependent types, then you can have a fully untyped language that's separate from your types. And so like Rolang doesn't care at all about the type of the return. And if someone has provided an or else that doesn't match the type, Rolang doesn't see that currently and doesn't care about it. And so, it would only be if you introduced some kind of typing scheme that would catch that. So if you do introduce an or else and the or else returns something that's not of the value part of the map, then you could potentially have cascading errors throughout your code. So, but Rolang doesn't care, and what the defensive coder would have to write checks, to make sure that whatever came back was of the right type. And they'd have to do that inside their code as opposed to having the compiler do it. And then if we introduce type checking, then the type checking would catch that. For expressions like this, which are essentially more functional in nature. Does that answer your question?
Yeah. So you're saying at this time, basically, if you use a .get or else and you deal with the or else properly and get on. So it sounds like.
I mean, you can think about
the defensive coder would take this .get and or else and bind it to a variable. So if we use Rolang 1.1 to simplify the discussion, then you would have a let, xg equal x.get or else something, and then that would be bound in xg. Then you check that xg has a binding that you accept, and if it does, then you put xg in here.
Mm-hmm. Okay.
For example, if X is really a map, right now with this something key, you can put any type as the value. So this get can sometimes return one type and another case return something else.
Exactly. And especially if you have an or else, because the or else allows you to supply the value that you're returning. So if someone who's calling the or else supplies the value that is not of the type of the value of the map, then you'll have a type mismatch, or you'll have, or in the case of Scala, what Scala would try to do is to find the nearest parent type, which always, finishes at top, right? So it would, that idea would work. You'll always get a type, but it might not be the type you want. But that solution gets thrown out the window as soon as you introduce dependent types. So you'd have to work at this in a different way as soon as you have dependent types. Does that answer your question?
Mm-hmm.
Cool. Good question.
I guess there are, there's a proposal here. I don't know if you want to look at it, of how to resolve this. And I think Tamsla still has a question or two. Do you, Tamsla? Or
we will definitely talk about this more.
Okay.
Yeah.
All right. Yeah, that's all I had on this.
Cool. Thanks. All right. See you guys in the developer stand-up. Thank you all.
Thank you. Bye-bye.
Thank you.